Welcome to Cybersecurity from Scratch, Technical Foundations, Episode 13, Network Architecture and Lateral Movement. In this episode, we'll go over some of the foundational technologies that we use to build networks, and then cover some of the basics in how lateral movement, from a red team perspective, works. We'll talk about some of the vectors that these red teamers use, and then we'll turn to the blue team and discuss how containment of attackers can be done. Now, we're only going to be touching on several of the vectors and technologies in this episode, and then we'll have several follow-up episodes right after this that get into those technologies in enough details that both red teamers and blue teamers can use them. To review briefly from a previous episode, network address translation, or NAT, is the technology that allows a network to be hidden behind a single public-facing IP, even though there are multiple computers and multiple IP addresses behind the network address translation layer. The wider world can only see a single public IP. The hosts behind this IP are able to connect outward to the wider internet, and then return traffic is routed back through that single IP. The great thing about this is you can have all of your hosts hidden behind there and essentially hide from the wider world what's going on in that network from a traffic perspective. It also makes penetration of that network much more difficult because essentially you need to convince the hosts inside that network to dial outward, unless there's a specific service which has been enabled to sit behind that public-facing IP. For more information, please review Episode 2. A network interface card, or NIC, allows a computer to connect to a network. In the old days, these were always physical cards, but now you can have a virtual card as well. For example, my laptop has a physical network interface card connected to a cable in my wall from which it connects to my router, while it also has a virtual network interface card to connect to the virtual machines that run on it. Computers often will have multiple network interfaces, often to different networks, and sometimes this can allow for bridging connections, where a particular computer can be set up to bridge multiple networks to access different services, or even to filter and control traffic between those networks. Computers use their network interface cards to connect to a local area network, or LAN. A LAN is simply a bunch of computers near each other, or local, which are networked together. Sometimes organizations need to have all the benefits of a LAN, with having computers networked together and all the security that provides, while those computers are separated and connected over the internet. In this case, you'll want to create a virtual private network, or VPN. Essentially what happens is there's an encrypted connection between the remote host and the network, and then that host is treated as being local to that network and is a trusted member of that network. Think LAN, but over distance. Now, as a policy choice, often secure VPN connections will force a disconnect from other networks. So if your computer is connecting to a VPN over the internet, it will only be allowed to connect to that VPN. Any other local area network that it's connected to will effectively be disconnected. This is kind of weird to think about because you're still connecting through the internet, and the internet is available through your LAN, but you're not able to route to anything that's not on that VPN. It's a little tricky to think about that way, but it ensures that effectively that computer, which is VPN'd in, can only access those specific resources you want it to, and no one's using it to bridge into the VPN. Let's add another level of complexity and mention that there's also something called a virtual LAN, or VLAN. Now, this is a distinct idea from a VPN. It's entirely different. The idea is that you're using software to create at the data link layer an entirely separate network. So what's happening is when you plug a computer into a switch, if it's set up to enable VLANs, it will determine if that computer should be on one particular VLAN or another. And so you have the effect of entirely separate LANs, but you don't actually need to run separate wires to make it happen. It's a pretty cool technology, and it's very effective in creating different security environments. Now, sometimes a computer will have multiple interfaces to multiple VLANs, just like with LANs, and can be used to bridge between them, which potentially is a way for someone to move between networks. Even though two computers are on the same LAN or VLAN, they may not necessarily be able to talk to each other. Sometimes a firewall can be set up or another piece of network can be configured in such a way that will permit or prohibit devices from exchanging traffic. And so you can have hosts that are on the same LAN and simply not be able to talk to each other. So for example, you could have a setup where a group of developer machines are on a LAN and they can only communicate with each other and are effectively separated from the rest of the network. They're still on the same network, but the rules are preventing traffic from going between them and any other set of systems. This is all very interesting, but what does it have to do with security? So at this point in the attack chain where the attacker is looking to move laterally, they've already enumerated a host, they found a way in, and they've compromised to an extent that they have an initial foothold. And so now there's really three tasks that they're going to look to do in parallel. They're going to be looking to see if they can escalate their privileges, if they need to go from whatever level of access they have to something else. They're going to look to persist their access, which is to say they can get back in if they ever get disconnected for some reason. And then they're looking to move laterally. Now, all three of these steps will often happen in parallel, or sometimes they'll be omitted depending on what the attacker is trying to do. If the attacker is just trying to get in and get access to information, oftentimes they'll be moving laterally without too much regard for establishing persistence or escalating privileges. They're just trying to move around as much as they can and get as much data as they can. It really depends on what the bad guy is trying to do and what his objectives are. Now, to move laterally, the attacker needs to repeat the enumeration phase with the new level of access that they have inside the host which is compromised, and from there figure out what LANs, VLANs, VPN connections, network interfaces, etc. are available to exploit, what can be accessed from those interface points in terms of services, and how they might reach out. This enumeration process looks a little something like the workflow on the screen. You check to see if there's multiple interface cards, to see if there's new places that you can connect to, just having new IP ranges to discover. So for example, if a host is compromised and you find a second NIC and a second IP range that wasn't previously routable, then there's a whole new set of attack surfaces to unlock. Additionally, even if there isn't a whole new network interface card implying that there's a whole other network to exploit, sometimes a particular host just has additional privileges to route to additional hosts, and so the attacker is going to look to rescan for new hosts, even if they don't see an obvious new network to exploit. And then finally, on any new network or that they're able to find, or new hosts that they're able to route to, they're going to repeat the same sort of host enumeration cycle that we discussed previously, scanning the host, determining what services are running, etc. To move within the network, there are a few different strategies that an attacker can take. Perhaps the easiest is to simply move normally through the network with the technologies that are designed to allow users to move around. We'll talk a little bit more about this in a second. The attacker can also establish a tunnel or proxy through a particular host to other targets, and this can be either used to use web attack tools or something like that. There's a whole science to tunneling TCP traffic, and we'll talk a little bit more about this later. The attacker can be positioning assets to attack other systems in the network or to exploit services. Moving files throughout a network in a way that is conducive to red team activities is its own science, and so it gets honestly its own episode. We'll discuss that in episode 13.2. And then finally, the attacker might be looking to tweak firewall assets on the local host that they've compromised in order to get more out of their pivot. And again, this is its own thing, so we'll talk about it in episode 13.3. Let's take care of the easy stuff first. So as an attacker moves throughout a network, they're building continuously a database of credentials that they've compromised. So that would be usernames and passwords, NTLM hashes. We'll talk more about that when we get to Active Directory, and any of their credential information that they have, like SSH keys. And they're continually retesting these credentials because often users are recycling those credentials elsewhere. And so something to remember is whenever you are using a password, the attacker can, if they ever compromise that service, reuse that password someplace else. So remember, password security is essential. There are a lot of different services on a network that can use username and password and allow an attacker to move around, but there are a few big ones that tend to be common compromise points. The first, especially in a Linux environment, is Secure Shell or SSH. This is the preferred solution for administrating systems over command line with Linux, and it can be supported on Windows with an install. There's a whole thing about SSH management, and we'll talk about this in episode 13.1, how it can be used for compromising systems, how it can be used as a tool for pivoting through a network, and so on and so forth. Remote desktop needs to be enabled, and by default on Windows it isn't, but should it be enabled, it's a very simple way for an attacker to pivot throughout a network. And then finally, a server message block, or SMB, provides a great way for attackers, particularly once they've compromised administrative credentials, to pivot through a network. For more information on that one, check out our previous episode, episode 12. Attackers will often, if they've compromised a host but can't find a way to use credentials they've already stolen to move within the network, simply set up a proxy to attack other services on hosts within the network. So what this might look like is if they've compromised, say, a system in accounting, and they've found that there's a website that allows them access to another division, but they can't access that website from the outside, they would set up a pivot point through the compromised accounting system and allow them to then directly attack the system in the division they're trying to access. There are a couple different ways to do this. A very simple proxy can be used with SOCAT, where SOCAT will listen on a particular port and direct traffic to another port. So it's just simply a bent pipe from the system that's compromised to the target host. If the attacker is using Metasploit, there's a very simple proxy command, the port forward command, which will allow them to set up an access point. Now, these are very simple port forwards. However, an attacker can also use an SSH tunnel to allow for a dynamic proxy server or for allowing other more complicated port forwarding approaches. We're going to talk about this in the SSH episode because it's complicated and there's a lot of considerations that go into it. Now let's look at the blue team side of things. Let's assume that someone has gotten into the network, they have a foothold, they're trying to move laterally. How do we slow down or stop them from doing that? Limiting any pivot point is essential. And this is specifically here talking about any box that can talk to two areas of a network which shouldn't directly be able to talk to each other. Consider, for example, you have departments A and B, which normally you don't want computers to route to each other, but you have a computer that needs to access resources from both of them. Now, do you want to have it set up so that that computer can directly address both departments A and B and have access to that information? Or does it make more sense to have the specific information from departments A and B sent out to some sort of DMZ from which the computer can access them? That way the computer doesn't need to directly access departments A or B, and there's no way to pivot through that attacking point into either department. The main idea is to make sure that there's no way for someone to compromise something in A and then go through the pivot point into B or vice versa. Generally, you want to apply the principle of least privilege to host visibilities. Really what you're trying to do here in this example is trying to figure out how to get a specific resource from departments A and B into the particular computer, and giving broader access that is not necessary for that objective is really just asking for trouble. Also think in terms of where users can log in. If a particular user is compromised, then any host that they can get access to is potentially a pivot point or a point that can be expanded into from another host. Many Windows-based organizations allow any recognized user to log in anywhere, applying permissions globally with Active Directory. And so what would happen in this situation is if you compromise some workstation in accounting and you have the information from that user, they can go anywhere in the organization because Active Directory will send those permissions everywhere. Really what you want to do is limit host login rights to the absolute minimum necessary. On the flip side, for Linux, you want to consider shell privileges. It's just so easy to allow users to SSH throughout the network, when in reality that's just another opportunity for someone to pivot through very, very easily. So what you would want to do is figure out which systems a user actually needs access to and block access, remote shell access that is, for any system where they aren't needed. And this can be done so that even if a user can log in locally, or if they have a persistent service that's running, they can't get a shell through from another host. Again, this is applying the principle of least privilege. If they don't need to access the host remotely, don't let them. Windows is visual, so remote desktop is the preferred way of getting around within a network if you're trying to get to another box. The good news is Microsoft allows very granular control over remote desktop. It can be disabled or enabled entirely via a registry setting. One strategy is for administrators to only turn it on when necessary and then turn it back off again using WMIC or another technology for remotely administering systems, and also allowing only specific users to be in the remote desktop users group. You want to be strategic with both the systems that can have remote desktop enabled as well as what users are allowed to utilize it. In this episode, we've mentioned a few technologies that attackers can use to move around the network, but we need more information to really utilize them in either an offensive or defensive way. And so for our next episode, we're going to be talking just about SSH, how it's used to move around a network in a red team capacity, as well as how blue teamers can configure SSH to be defensive.